So here we're going to be able to see the radiation pattern of a finite dipole antenna as a function of the length of the antenna. You can see in the title up here at the top of this plot that the length of the antenna is currently set at 10% of the wavelength of the signal. And while that doesn't strictly qualify as an infinitesimal dipole antenna, it's as close as we're going to get in this animation. So I just want to take a minute and point out that at the very center of this plot, at the bullseye there, you can see there's a tiny, tiny little figure 8. And that figure 8 represents the radiation pattern of what is approximately an infinitesimal dipole antenna. Now it's so small because the radiation that is emitted by an infinitesimal dipole antenna is so low. This is one of several reasons why an infinitesimal dipole is just a terrible antenna. So we're not going to be using an infinitesimal dipole for anything other than deriving the relationship of a finite dipole antenna. So as we begin to increase the length of the antenna, I want you to see that that figure 8 is going to grow, and that's going to represent the fact that the antenna is doing a more effective job of transmitting electromagnetic radiation for the same level of input that's being applied to the antenna. So let me go ahead and see if I can, and now we're going to be able to see the radiation pattern is growing. Pretty soon here we're going to cross through the half wave dipole, and that's right there. That's the half wave dipole. You can see that we're still getting this figure 8, or this sort of sideways infinity that's perpendicular to the direction of the antenna itself. Now it's beginning to narrow down. Now we're at the place where the length of the antenna is equal to the wavelength of the signal. Oh, here comes some side lobes, and the main lobes are beginning to shrink down. And so you can see now at this moment we have 6 lobes that are going on. We're at 1.5 lambda. Looks like a butterfly right there. What used to be the main lobes are now side lobes, and they're shrinking down to basically 0. And as we get up to 2 lambda for the length, now those four main lobes are going to begin to shrink down. We're going to pick up 6 more lobes. So for a moment here, we're going to have 10 lobes that are coming out right there, 10 lobes, all not quite exactly equal in amplitude, but fairly close. And as we approach L equals 3 lambda, we're now going to end up with 6 lobes here. So and the animation stops at 3 lambda. Just notice here that now we've 6 very narrow lobes. And for example, if we were to find a way to physically block 5 of those lobes, then right here, for example, this top lobe is at 90 degrees. That's extremely narrow. And in some cases of an antenna, you want an extremely narrow or an extremely directed antenna. And so this might be a place where we'd want to be able to use something like that. There are other reasons why we might not choose to use L equals 3 lambda other than the radiation pattern. And in general, we're going to find that L equals 0.5 lambda is a very desirable antenna.